Hello and welcome to this video. So today we are going to be talking about the capacitance and impedance of dielectrics. This video is from the point of view of a materials scientist, not going to do so much details as like an electrical engineer would want to, but just let's get like a clear understanding of the basic concepts. So I will start this presentation to talk about why capacitance is important, what is the reason we are trying to measure capacitance and how we use that to characterize dielectric materials, and we will talk about simple circuit elements that we need to understand and how the capacitance, resistance, and impedance relates to these simple circuit elements, and then we will use these simple circuit elements to build equivalent circuits which we can use to model real systems with, and we can use to actually characterize our materials based on these equivalent circuits. So the capacitance is a very important property of dielectrics. So for example, field effect transistors need a dielectric, capacitors of course need dielectrics, and many other electrical devices. And the capacitance is going to be what tells you that like how the electric field and the accumulated charge density or charge number of charges, or the just generally the how large the charge is at specific electric field. So if we are taking a look at a field effect transistor, which is one of the things that I was studying previously, the field effect transistor will have like a gate electrode in the bottom here. So this gate electrode will be biased with, so this case it's with a negative voltage, and then we have like the source electrode here, which will be the charge source, and the drain electrode, which will be the electrode where we remove the charges. So the current, as you can see, is flowing from the source to the drain here. The gate electrode is regulating the current flow. So the higher electrical potential or higher voltage is put on the gate electrode. That will mean the higher number of charge carriers will be accumulated in the semiconductor. So this is the semiconductor, this is the dielectric. And the more charges or the higher number of charge carriers is accumulated in the semiconductor, the higher the current is. So generally, if we have like a good dielectric, it will generate higher number of charge carriers under the same amount of voltage, and that is what the capacitance will be related to. Let's take a look at the simple circuit elements. The field effect transistor is definitely not a simple one. So we have resistors. In a resistor we have the current flowing through, and the current, which is I, will be related to the bias or the voltage between these two terminals by the R, the resistance, and this is Ohm's law. So capacitor is going to have these two plates, and on one of the plates the positive and the other plates the negative charges will be accumulated. And in the capacitance case, the capacitance is going to describe the ratio of the charges accumulated to the voltage. So higher voltage, the higher number of charge carriers, the higher capacitance, higher number of charge carriers will be accumulated under the same voltage. In the inductor case, we have the current flowing in this kind of spiral motion, which will generate this magnetic field around. And the magnetic field is this phi b. This is a magnetic flux, and that is related to the current using this inductance variable, or inductance constant rather, for this inductor. So inductor, basically we can say the inductor stores energy in magnetic field like this, as the current is flowing through, and the capacitor is storing energy in electric field. So between these plates there will be an electric field due to the plus and the minus charges on the two sides of the capacitor. So the capacitance is of course going, as I said, they will relate this Q and this V values together. So the voltage and the charge carrier density, or number of charge carriers, or rather just charge on the plates here. So of course, the higher the area of these plates, the capacitance will be higher. And then this is the E0, this is the vacuum permittivity, so this is one of the constants of the universe, we cannot do anything about that, but this K value will describe the dielectric, and the higher the K value, the higher the capacitance, and the higher the capacitance, higher the number of accumulated charges. And we also have this D, which is going to be the distance between the plates, so the further these plates are apart, the smaller the capacitance will be. So, of course, to have this charge separation here, we need to put in work, and this is going to be generating this electric field. So the ideal capacitor, of course, will have no current flowing through. Of course, ideal capacitors don't exist, but in an ideal capacitor case, the higher the voltage, the higher the number of charge carriers, or the larger the charge will be, and no current will be flowing between these two plates. Alright, so let's go back to the resistor. So the electrical resistance is basically, as we said, relates the current and the voltage. So higher the voltage, of course, the higher the current. So you can see both cases the current is linearly going up. This is Ohm's law. But the higher resistance will mean, so this is a higher resistance with the black, will mean that under the same voltage, the current will be lower than for the resistor which has the lower resistance. So this is basically what we mean by resistance, is that the resistor resists the current to flow through. So this is a high resistance case here with the black, and the high resistance device will not it will resist the current more, so the current that's flowing through is lower. We are resisting the current. So capacitor, if we have the capacitor under the direct current, there will be something very different here. So can I change my pen color here to black? Yeah, so here, if we turn on the voltage, so let's say this is as a x-axis is time, so we turn on the voltage and then keep the voltage same. What will happen? And let me go back to the red here. So from this side, the positive charges will come to the capacitor, and from the other side, from the negative pole here, the negative charges will start filling up the other plate here, which means the current, of course, will go up, but as soon as the number of charge carriers reaches the equilibrium state, which is what will be defined by the capacitance, so how many charges will be here in equilibrium under a certain voltage, that then suddenly, so you can see on the bottom here we have a negative polarity electrode, and now this plate also has a large negative charge, so negative charge carriers cannot move here, positive charge carriers cannot move there anymore. So what we have is that this current will go down to zero. No more current is flowing through the device here. So under direct current, we just charge up the capacitor, and the capacitor stays charged. So this is, in this case, we cannot really measure. What do we measure? Do you want to measure this very short current spike here? It's very difficult. So this is why we don't really measure capacitance under direct current. Instead, and in the alternating current, I'm not going to draw this, but I will tell you that once we start giving like a positive bias here, what is happening, the positive charges will be moving towards this plate. So positive charges will be accumulating here, and then the negative charges will be accumulating here. So the current is flowing towards like this, in this direction. And then when we change the polarity, so the polarity changes in alternating current going positive, negative, positive, negative. Once we change the polarity to negative, or going towards the negative, then suddenly these plates are charged too much positively, and these plates are charged too much negatively. So the charges will start moving in the opposite direction, and someone already drew it better than me. So you can see that once the voltage is going up, then the current is going down, and as the voltage is going down, the current is going to the negative here. So as the voltage is moving towards the negative polarity, then we have a current going in the opposite direction, and once it reaches the maximum or negative, then of course this top plate will be charged with negative charges, the bottom plate will be charged with positive charges, and as the current starts, or the voltage starts going back towards the positive direction up here, now the negative charges will be leaving the plate. So nice macro in the editing room here. So what I forgot to say here is that basically in this case, like for example, when we talk about the negative current here, so part of this negative current will be, for example, positive charges moving out of the plate, and part of it might be when the negative charges are moving towards the plate, but this is basically equivalent, so positive charges moving up or negative charges moving down, that is the same direction of the current. So you can see here that the current, which is the red here, is shifted to the left. So because it's time and the time is flowing in the from left to right here, we can see that the current is ahead of the voltage. So the current is higher first, and then the voltage is going up later. And this is exactly shifted by pi over 2. So pi over 2 is based on, like, this is called the phase of the sine curve. So phase, if you don't know, the sine curve is going up and down like this, and we can relate it to like a circular motion. So circular motion, of course, is going in a circle, and this is the x-axis is going to be the 0, and when we reach up here, that's going to be pi over 2. So that's basically the angle in radians. So once we reach like to here, that's pi, and then this is like when we go back to 0, that's also 2 pi. So 2 pi is 360 degrees. And the phase, so we can describe how as we are moving in this circular motion, we are going up here on the, what is this, the y-axis, and that is going to be the sine, and then the cosine is the x-axis of this position. So we relate the angle of the circular motion to the position of in time of this sine curve. So why we do this is because this is time, but we can have different frequencies. So some of the way like goes faster, some will go slower, but we always have the peaks and the troughs, and we can always say this is 0 and then this is pi, and then when we reach this back to complete one cycle, that's 2 pi. It doesn't matter how long this period takes. What matters is like the positions of the curves here that is described here, and based on this, in the capacitor, it is always, the current is always shifted by pi over 2. So now we can go to the next slide. Here we describe the maximum current related to the maximum voltage. So if we go back here, we can see that there is a maximum current and there is a maximum voltage, Vm and Im. And if the frequency is higher, that means this kind of the plus to minus to plus is going faster, and then the charge carriers will move back and forth faster. So that will mean that as the frequency is higher, the current, the maximum current will be higher. Of course, capacitance is also in here, and omega is just basically 2 pi times frequency. So we are relating the sine wave to the circular motion here with this 2 pi f. It's easier calculation. And because we had this I equals V over R for the resistance of a simple resistor, we want to make like a similar relationship here between the maximum current and the maximum voltage, and that will be the XC. So XC is basically 1 over omega C. So this XC will depend on the alternating current frequency and the capacitance together. And this Xc is what we will call capacitive reactance. So this is not just resistance, because resistance, we say the resistor is resisting the current. So higher resistance means it resists the current more. This is not just that, it's reactance because there is some kind of the reaction time here. It's like faster. It's reacting before actually the voltage is going up. We can think it like that. So the capacitor case, we can say this is like 90 degrees shifted. So pi over 2 is 90 degrees. And the resistor case, the current is 0 degrees shifted, because in the resistor case, if my, this is our very nice coordinate system, when the voltage goes up, voltage goes to minus, then what we'll have here is the current will just move together. So every point, the ratio between the current and the voltage will be described by this equation. So it's 0 degrees shifted. It's going up together. Capacitor case, this equation is only valid for the maximums, and there is a 90 degrees shift. So now we have two things we have to know in our circuit. First of all, how much is the maximum current and the maximum voltage related to each other? What is the relationship? What is the ratio? That is like a size, and then the angle. How much is it shifted, positive or negatively? So we have an angle, we have a size. That is something we can describe with complex numbers. So instead of having two numbers, which is a size and an angle, we use a complex number, which is just made up of two numbers. So how that will work is that we have the resistance as the x-axis, reactance as the y-axis, and the resistor here is always at this point. So this is the origin, and this is like a 0 degrees, so there is no shift, and the resistor is independent of the frequency. It's always same resistance. On the other hand, inductor case will have like a positive reactance, which will depend on the frequency, and this will be always like up 90 degrees. Capacitor case always down 90 degrees, and this is also, as we could see, it depends on the frequency. And so resistance will be the real part of the complex number, and the imaginary part will be the reactance. So when the reactance is the capacitive reactance will be negative and the inductive reactance will be positive. And so putting these two imaginary and the real numbers together, we will get Z or Z, which is the impedance, and the unit will be ohm, same as for the resistance. Okay, so now moving towards equivalent circuits, because life is not easy. Of course, when we are trying to measure the dielectric constants of real dielectrics and we make a capacitor to do that measurement, we will not have an ideal capacitor because it is connected to a power source which with a wire. So this wire will have some inductance where where the connections are, and it will also have some electrical resistance. So what we need to do is we need to take into account that there is some equivalent series inductance, which is ESL, because L for inductance, L is the symbol for inductance, and then we have equivalent series resistance, which is called ESR. So this we sometimes call RS because it's like series resistance. And then of course we have the capacitance of our capacitor, which is C or CS. And this is basically the simplified RLC model, because resistor, inductor, and capacitor, so RLC model. But usually this ESL, so the inductance, can be ignored except for high frequencies. So this is only going to affect our measurement at high frequencies. At low frequencies we can say it's 0. So if we take a look at this graph here on the right hand side, you can see we have a 1 kilo ohm series resistance and a 15 nanofarad series capacitor. And usually, because we work with capacitors more than with inductors, we put this negative sign over here. So the imaginary part is in negative. So instead of going down, it is going to go up. And we usually start the measurements at high frequencies. And at high frequency, the current is much higher. So we can remember that high frequency case, the voltage on the two sides of the capacitor change faster, so the current will be higher, and the higher current means lower capacitive reactance. So high frequency means we will get these points very close to zero. So this is zero here for the imaginary axis, and we will have the real axis exactly at the resistance of our series resistor. And as the current, or as the frequency rather, going down, the capacitive reactance is going to go up because the current is going down, so the capacitor is like resisting or reacting to the current in that way. But this is of course a very simple simplification. In general, even the best dielectrics will have some leakage current, so we need like not just a series resistance, but there is like a conductance of this dielectric, so some of the parasitic current or leakage current will flow through. So of course conductance is just like the inverse of the resistance, so there's not much going on here. But if we have 1 kilo ohm for the series resistance and then 5 kilo ohm for the capacitor itself, and then we keep this 50 nanofarad the same, and you can see even in this graph we have the exact same axis. So you can see that at high frequencies we have basically the same thing going on here, and as the frequency is going down, the capacitive reactance will kind of change, but then suddenly starts going down as the resistance of this parallel resistor will have a higher and higher effect on this circuit. How you should understand it is that, so for example, if we have like a parallel resistors and one of them is much smaller than the other, so let's say this R1 and this is R2, and R2 is much smaller than R1. In that case, what we will have is most of the current will move this way, right? So some of the current will go towards the higher resistance, but most of the current will flow through the lower resistance resistor. And the same thing will happen here. As the frequency is going down, then the capacitive reactance of the capacitor itself would go up. So most of the current will just go through the dielectric, which means that the equivalence, like capacitive resistance for the whole circuit, will be going down, while the resistance, like the real part of the impedance, is going up. So we will have this kind of a semicircle. So this semicircle will start at 0 in the imaginary part of the impedance, and it would go back to 0 at like infinitely small frequencies. And what we need to see here is that this 1 kilo ohm is the RS, and then up here to 6, this is 1 plus 5, so this is going to be the parallel RP or whatever, 1 over GD. So this is the parallel resistance, will be the diameter of this semicircle, and the starting point of this semicircle at high frequencies will be the RS, the series resistor, or the lead resistor, lead resistance. And this is basically what I'm saying, like moving this way, because usually when we measure the capacitance, we start with the high frequency and then we go down towards the low frequency. So don't get confused about that. So now let's take a look at the next slide here. So usually when we measure the capacitance, or we measure the impedance rather, we just calculate the series resistance and the series capacitance. So we can just assume this very simple circuit here with the resistor and the capacitor only. And if that is what we do, then of course when we are actually having a leakage current, what will happen is that at every point, so let's take this point here. So if we compare it to our previous one, to the simplified RCL model, its every point is basically you can say the x coordinate is just the RC, and from this is going to be the x. So the capacitive reactance here, and from the capacitive reactance you can calculate the capacitance directly. But once we have this more complicated circuit, then the x axis here will be, for the resistivity, will be somewhere in the middle, and then we will have this capacitive reactance here. But this capacitive reactance is not going to directly give us this capacitance here, because this is not going up straight line. This is going up this is going in a semicircle. So what we can get here is that if we really don't have a leakage, then this is a capacitance and this is resistance. No leakage, so it is really series resistance and series capacitance. So every frequency, same value, we can get it. Of course, when real measurement, there is always some noise, so there will be ups and downs, but in general, you should just get straight lines. On the other hand, when there is leakage, we have the straight lines at the high frequency, because in the high frequency part here, we can see it's just going up, and it starts to deviate a little to the right, and that frequency, the capacitance, the measured series capacitance will start to go up, measured series resistance will go up. And when we get this, so some people will just say that, oh, the capacitance is unstable at low frequencies. That is not true. The capacitance of the capacitor, or if you calculate the dielectric constant, if you calculate the dielectric constant for this from the capacitance, is not going anywhere. What is unstable here is that our approximation of using only RS and CS is not working. So this one is actually not a measurement error, not instability in capacitance and resistance in our material. This is just simply we are using the wrong model. And some of the experimental equipment, you can actually just measure impedance, and it will let you fit a semicircle here, and based on this semicircle, it will give you exactly your C and R and G or two R values if you want it as a resistance value. Alright, so this is what we get, and then let's go back and check out the inductance. So in the start, we talked about how the inductance is only affecting our measurement at high frequencies. So you can see that if we have inductor, that means, okay, suddenly in this case I didn't put the minus sign here, but rather here. But anyways, we can see that at high frequencies, because the inductive reactance is a positive value, the high frequencies will start from here, and as the frequency is going down, we'll go back to the negative regime. And in this case, when we have an L of 0.01 millih, then it will reach 0 at 2 times 10 to the 5 hertz, which is incidentally here. So what we will get when we just try to plot it as RS and CS, so series resistance and the series capacitance, what we get is we have a negative capacitance over a certain frequency, and then this capacitance suddenly goes up very high, and then it will go very low, or not very low, rather, it will go back. And this part, once we reach a sufficiently low frequency, then what we will have is this capacitance will be around the real capacitance, just like we had for the leakage current here. The capacitance we have at this high frequency part, it is going to correspond. So this should be 50 nanofarad, and there is that, and this also should be 50 nanofarad, and there is that. But of course, once you have this inductance and you also have the leakage current, then let me change my pen color to a little bluer. Then of course you will have the same problem at the low frequencies, and the higher your leakage is and the higher your inductance is, the smaller this area where you can actually see the real capacitance on this plot will be. So this is why I personally always prefer to plot the impedance, draw up this equivalent circuit, and let the software, so specifically the impedance measurement software, usually lets you make this model circuit, and it will fit the curve and then calculate you everything you need. Okay, so this was the video on impedance for material scientists. If you liked it, give me a like, subscribe for more content, and leave a comment down below if you have any questions or if you want me to cover other material science and related topics. And see you next time, I guess. Have fun. Bye bye.